Okay, so first, I just want to say welcome to the FODSI sublinear workshop. I think there's some, I guess the first sublinear workshop was like 22 years ago. And we're still the same group of people. It's still, sublinear time, streaming, sketching. It's the same people. And I once told this to Jennifer Chase, and she told me that most marriages don't last this long. But I think it's a very happy marriage. And I hope you'll see that the talks here, they look like they're going to be amazing. And I can't wait to see them all. And the workshop has to go from everybody gets to give an hour talk and we get big breaks. And now we give short talks because we want to get a lot of people in. And all the talks are incredible. And anyway, enjoy. I should shut up so that Andrew can speak. And so I'd like to introduce Andrew McGregor. I think we're going to keep the introductions short in this workshop. So I'm just telling you his name. And he'll be speaking on reconstructing graphs from random subgraphs. And we're happy to have you. Take it away.
Thanks very much, Ronit, and thanks very much to the organizers for inviting me. And I'm so sorry I cannot be there in person today. So as a bit of a curveball, I'm actually not going to talk about a streaming algorithm. I'm going to talk about something which is more based around sampling and analyzing the sample complexity of a certain problem. And the problem I'm going to look at is what I think is a kind of a fun, natural problem that I've been looking at with one of my grad students, Rick and Gupta, on reconstructing graphs giving from samples of random subgraphs. Okay, so the setup is as follows. So we have this unknown graph on n nodes. Typically n is bigger than 6, and we don't know the unknown graph, unsurprisingly, but we get to observe a trace. Now, what is a trace? A trace is a random subgraph, so every node has been deleted independently with probability of half and all instant edges removed. Okay, so this is a trace you see. Okay, now you don't just get one trace, you get 2, 3, or maybe many traces. And the question I want to look at is how many traces are required for you to be able to look at your observed traces and infer back the unknown graph. Okay, so I want to emphasize that our graphs aren't labeled. They kind of, like when you use a trace, you literally see something like this. If the graph was labeled, this would be a way easier problem. In fact, you could, fairly straightforward argument would allow you to conclude that kind of log n traces were sufficient. But in our setting, no labels. Okay. So I want to kind of build up to the problem by relating, or building up to our results by relating it to some other kind of well-known inference tasks. I will start off with the most basic one that I'm sure everyone has seen. So you have a coin with an unknown bias. Probably the first thing you learn like in a TCS class or early on in the TCS class is that with roughly 1 over epsilon squared flips, you can learn the bias up and add to epsilon. Okay, slightly more involved, but not really. If you have a distribution with an unknown distribution with standard deviation sigma, roughly sigma squared divided by epsilon squared samples is sufficient to estimate the mean up to plus minus epsilon. Okay, so to relate this to graphs, let's consider a graph whose only edges form a star, and that star has d leaves. How many samples are required to learn d? So here's our picture. Here's the original graph. Here's a trace, here's a trace, here's a trace. And notice that if the original graph, if the star had degree 3, then the degree is kind of gone down to 2 in this case, 2 in this case, 1 in this case. So basically in each trace, you're getting a sample from the binomial distribution with parameter d, comma, a half. Okay. And using that second bullet and the standard deviation of the binomial distribution, you can conclude that if you have d traces, then you'll be able to kind of work out what the degree of this graph is. And for this special family of graphs, that was all there was to learn, the degree of the single star in the graph. Okay. I should say I'm kind of glossing over like kind of technicalities, like kind of, well, in some of these traces, it's conceivable that the center of the star could disappear, but I'm not going to worry about that sort of stuff in the introduction. Okay, a more involved inference task arises when you talk about mixtures of distributions. So a mixture distribution M is formed when you've got k component distributions, for example, k different normal distributions with different means, maybe this is the same or different variances. And a sample from a mixed distribution is formed by picking one of your components, one of these k components uniformly at random, and then returning a sample from that particular distribution. Okay, and there's a whole bunch of work in the TCS and ML community on working at the sample complexity and efficient algorithms for either exactly for learning these means or for finding distributions which are close to the distribution formed by that mixture. Okay, and so again, to relate this to graphs, learning parameters or mixed distributions is kind of similar to learning degrees of multiple disjoint stars in the following sense. So let's say our original graph had these 3 stars of degrees 3, 3, and 2. In your first trace, well, the degrees have become 2, 2, and I guess 1. So you get these degrees, and then it came from these degrees. But notice that we don't know, like, kind of, because the graphs themselves aren't labeled, we don't know whether this degree 2 is coming from something that was originally degree 2 or degree 3. There's no ways to kind of associate one of these stars with the star here. In the same way that when you have a mixed distribution, when you see your final sample, you don't know which component it was from. Okay, so the only real difference here is, like, kind of, in the graph case, maybe you get multiple samples from different components, but you still don't know which sample came from which component. Okay. Okay. The last thing I want to kind of mention, kind of leading up to our results, is a more kind of combinatorial kind of reconstruction problem, which is which arises in the context of the deletion channel and the study of information theory. So we assume that Alice has a length n binary string, say an arbitrary 0-1 string, and she sends it through the deletion channel to Bob. Okay, and every time she sends it, like, kind of, each bit is deleted with probability half. So Bob ends up with a random substring of Alice's string, but she'll send it multiple times. So Bob gets multiple substrings of the initial string. And the question in string reconstruction, also referred to as trace reconstruction, is how many of these retransmissions are sufficient to reconstruct X. Now, I realized kind of yesterday that, well, I didn't realize yesterday, I've known for quite some time. This was like kind of, the study of trace reconstruction was, I guess, was one of my first papers in grad school. I realized, like, yesterday with some horror that it's like kind of almost exactly 17 years ago, that I first started looking at kind of string reconstruction. I'm now looking at graph reconstruction. And I'm reminded that kind of cicadas come out every 17 years to kind of do what cicadas do. And so I find this figure reminiscent of that. Okay, so that was the problem we were looking at. It's going to be related to graphs. I'll get to that in a second. When we first mentioned this paper, by the way, this was a problem that no one seemed to care about for the longest time. So to all the PhD students who find no one citing your work for like 15, 16 years, let this give you hope that maybe one day someone will care about what you work on. Okay, so, but now there's a whole bunch of work on string and trace reconstruction, but the problem's still wide open. To reconstruct an arbitrary string X, the lower bound of the number of transmissions required is polynomial, the upper bound is exponential. Even if we look at the average case when we assume that X is random, the lower bound is like kind of polylog, the upper bound is substantially above polylog. Okay. So what do I want to talk about today? I want to talk about graphs. I'm going to tie some of this into string reconstruction and mixtures. I'm going to start off talking about arbitrary graphs. And my first thing I'm going to talk about is kind of bad news. That it's kind of trivial that an exponential and n number of traces suffice to reconstruct an arbitrary graph, just because if you take an exponential and n traces, well, there'll probably be at least one copy when no nodes were deleted. That makes life easy. But the bad news is there exist some graphs or pairs of graphs that if you have to distinguish which graph is is the unknown graph, then you're going to require exponential, the lower bound is also exponential and n traces. So this is kind of bad news I'm starting with. I'm a great fan of parties, by the way. The one kind of, there are some things you can still do with arbitrary graphs. So for example, you'll be able to learn degree distributions in exponential in the cube root of n number of traces. Okay, we'll then move on to random graphs, where the story is much happier. Like for almost all graphs, we'll be able to show that order log n traces suffice. And this is optimal, okay? These emojis are meant to indicate how happy you should be about that part of the talk. And in the last part of the talk, I'm going to talk about a slight variant of the problem where I'm not going to be talking about the graphs, but I'm going to be talking about adjacency matrices. I'll be more specific when I get to that part of the talk. But we're going to have two main results. That for arbitrary graphs, exponential in n to the 2/3 traces suffice, and for sparse graphs, specifically kind of graphs with constant degeneracy or constant arboricity, exponential in cube root of n traces suffice. Okay, so that's what I'm going to talk about. Again, I'm so sorry I'm not there in person, but if you have questions, I'm sure if you shout loud enough, I will hear them and I will try and address them. Okay, so let's start off with arbitrary graphs. Okay, so as I said, like kind of, if you start with an arbitrary graph, then it's kind of the trivial, there's a trivial upper bound of exponential n. And so the first thing we'll talk about is that this trivial bound is essentially optimal. And this is actually not too hard to argue. The idea is to look at two specific graphs, graph A and B. A is a cycle of n nodes, and graph B is a cycle, is two disjoint cycles, two node disjoint cycles, each on n over 2 nodes. Okay. Now, we're passing one of these graphs through the deletion channel, or rather we're getting these random subgraphs. Now you can't be sure which one is the unknown graph until you see n over 2 adjacent nodes that weren't deleted, okay? Because if there's n over 2 nodes that weren't deleted, in this case, like you'd be seeing that cycle of edges, where in this case, you'd just be seeing a path, okay? Now, because each node is deleted with probability of half, it's not hard to argue that you need to repeat this like an exponential n times until you see that that sequence of n over 2 adjacent nodes not deleted. Now, of course, this is just to be sure, but if you wanted to argue about kind of error probabilities, what you can do is you can just show that the distribution of subgraphs you get from this graph is incredibly close to the distribution of subgraphs you get from this graph and get your lower bound that way. So I won't do that. I don't think there's much use to it. But this is essentially, in a nutshell, why it's hard to deal with arbitrary graphs. Okay, so the result is also somewhat unsurprising, since there's this famous conjecture in graph theory that's called the Reconstruction conjecture that's been open for general graphs for like 60 odd years, and that's been resolved for some specific classes of graphs. The Reconstruction conjecture asks, well, does having all proper subgraphs, all proper induced subgraphs, determine the original graph? And so if we proved an upper bound less than exponential n, in that case, you could argue that you were reconstructing the graph from a bunch of subgraphs while never having the original graph. So you have even less than all the proper subgraphs, and you'd be reconstructing the graph. Okay. So that's the bad news. As I said, there's some slightly positive results if you want to be optimistic. I guess there's one of the things that's particularly nasty about this lower bound is that it's even applying to graphs of degree 2, to kind of planar graphs of degree 2. If the graphs just had maximum degree 1, life would be pretty easy. Like, what's a graph with maximum degree 1? Well, it's matching. So let's say, well, it's a matching in some isolated nodes. If the graph consists of k disjoint edges for some known k, then the number of disjoint edges in the trace is distributed as binomial k, a quarter. So again, using previous arguments, we could kind of we could work out k exactly with order k samples, or k could be as much as n, so order n samples. Slightly more interesting is what I mentioned about learning the degree distribution. And there the idea is to relate the problem to learning a mixture of distributions. So for example, let's say we have our unknown graph, we receive our trace, pick a random node in your trace and tell me the degree of that node in the trace. Well, that's actually the same process as having n different binomial distributions with parameters d1.5, d2.5, or dn.5, drawing one of them uniformly at random, and giving back a sample from that distribution. And it's possible to show that you can learn a binomial distribution in exponential in n to the third samples. And I'll talk a little bit about that in a second. Okay, so as I said, for arbitrary graphs, most of the news is bad. For random graphs, however, which is what we'll get to in a second, the news is going to be much better. But I want to first of all kind of dig into this learning mixtures results a little bit further, both because some nice, if you haven't seen it, some nice standalone learning can be done in one slide, and also because I'll come back to it at the end of the, I'll talk about some generalizations of it towards the end of the talk. So we've reduced, so all I've said so far is we can reduce the problem of learning the degrees to learning the parameters of a mixture of binomial distributions, and there's a result that says you can learn the parameters of a mixture of distributions in exponential and n to the third samples. So let me just talk about like kind of the learning between, like learning a mixture of distributions. It's very much related to a technique that arose by a couple of authors proposed in the context of trace reconstruction. So I'm just going to recap that here. So the setting is, I'm going to translate everything into the context of learning mixtures though. Okay, so we have one distribution X, which is a uniform mixture of, say, these n component binomial distributions where A1 with parameters A1 up to AN. In the context of graphs, A1 to AN would be degrees of a graph. And Y is another mixture, this time with parameters B1 up to B2. And I'm just going to talk about the challenge of distinguishing X from Y. It turns out the problem from distinguishing two mixtures of binomials is if you can solve that problem well, you can pretty much solve the problem of actually learning the parameters, but I won't go into that. Okay. So standard results, if you have two distributions with variational or L1 difference between them, and then the number of samples that you require to distinguish them is roughly 1 over the square of that variational distance. Okay, so roughly 1 over L1 difference between the distribution of X and distribution of Y squared samples is sufficient to distinguish X and Y. So what we need to do is we need to basically just argue that the variational distance is not ridiculously tiny. It's only somewhat tiny. And then we'll get an upper bound on the sample complexity. So the main idea of this prior work is to look at characteristic functions. And characteristic functions are really just like kind of, we're going to be slightly more general than characteristic function. We're going to think about W being a complex value. Normally we think about W being a unit convex number, but in our context, it could be larger. And we'll look at the expectation of W to the X. We can actually rewrite the expectation of W to the X in this following nice form, which it just ends up being 1 over n times a kind of a polynomial in Z, where Z is related to W in a fairly straightforward way. And the degrees in this polynomial relate to the parameters of the mixture distribution for X. Okay. Okay. So to get a handle on the variational distance between X and Y, we can look at the difference between the expectation of W to the X and expectation of W to the Y. Following from this above bullet, we can write that as in this form. And then it's fairly straightforward to show that if you have a function, then the expectation of a function f of X and the difference between that and the expectation of function of y is at most the variational distance times the maximum value the function can take, which in this case is this w to the n. Okay, so we can upper bound this difference in terms of the variational differences, which is what we want to get a handle on. As we have this lower bound, and this lower bound is all about a polynomial which has coefficients. This polynomial here has coefficients basically 1, 0, or -1, ignoring this whatever n factor. This is what's called a Littlewood polynomial, and it's an object that's been studied a fair amount by the combinatorics community. So if we want to find a lower bound on this variational distance, we want to ensure that this polynomial is not too small and this value is not too large, because then when we divide through by it, we'll get a decent bound on the variational distance. Well, there's this lemma that says, sure, like, for any polynomial where the coefficients are +1, -1, or 0, you can end up, you can find a value z, equivalently a value w, such that f of z is not ridiculously tiny and w is not ridiculously large. And so picking a specific kind of parameter to plug into this argument, we get that the variational distance is at most this quantity, which was this, divided by this to the n, which gives us the variational distance between x and y is bigger than some quantity. So let's say, like, this line of argument kind of appears in a couple of places in prior work in trace reconstruction. But so all I've done here is I've mapped it to the language of mixtures. But I'll come back to this towards the end and talk about an extension. Okay, so random graphs, which is where we had somewhat good news. Okay, so for almost all graphs, order log n traces suffice. And this is optimal because it's the best we could hope for, because if every node is deleted with probability of half, you're going to need omega log n traces just to ensure that every node shows up at least once. Okay, which is of course a necessary condition if you're ever going to kind of do reconstruction, because you'll need to know what that node was adjacent to. Okay, and the basic approach at a high level is remembering that reconstruction is easy if the nodes were labeled. So we want to kind of leverage the randomness of the graph so that we can kind of basically label the nodes that we get in the traces and then proceed from there. So let me tell you how to do that. Okay, first of all, a couple of definitions and a nice result about random graphs. So start off with graph G. I'm going to say G has identical subgraphs of size T if for two subsets of the nodes, two subsets of the same size of size T, that we have that the induced subgraph on U1 equals the induced subgraph on U2. Okay, so if you like, kind of, I'm talking about kind of the graphs being isomorphic, but I've had big arguments with my my co-author whether we should, for unlabeled graphs, whether we should call them be isomorphic or equal. But I hope you know what I mean. So so the picture, like, kind of, V was all the nodes of the graph. U1 is some subset of nodes over there. U2 is some subset over there. Let's say if I looked at this induced graph, I get the star of degree 3. If I looked at this induced graph, a star of degree 3. In that case, I would say that G has identical subgraphs of size T, of size 3. Sorry, 4. Help if I could count. Okay, next definition. A graph is asymmetric if there's no node labeling that yields the same set of pairs of labels assigned to edges. Okay, which is basically that the only kind of isomorphism is the automorphism. Okay, so symmetric graph, an example would be this graph here. I'm going to kind of label it for the sake of being clear in my definition. So notice that if I swap the labels of node 4 and node 1 and labels of node 6 and node 5, I would end up with the same graph. Okay. Whereas in this case, the graph on the right, there's no way to kind of relabel the nodes so that I end up with the same graph. So this is an asymmetric graph. This is symmetric graph. Okay. So a nice result, existing result from a random graph theory is Muller's theorem that says a random graph, by which I will mean a Schrödinger graph with parameters n². And a random graph has no identical subgraphs of size a constant more than n/2, and all subgraphs of size substantially more than n/2 are asymmetric. Okay, so we're going to use this result kind of heavily, and then we're going to need to extend it to actually get our final result. Okay, so the basic idea is that so we take multiple traces, so multiple subgraphs, and we want to color the nodes in each trace consistently. And what do we mean by consistently? I mean that if a certain node U is present in trace 1 and trace 2, I'm going to color the instance of U in trace 1 and the instance in trace 2, and it's a consistent coloring if the colors are always going to be the same. If the two nodes in the two different traces came from the same original node, they should be getting the same color. Okay, so again, for the sake of a picture, here's the original graph. Let's say these 3 nodes survived in the left trace, these 4 nodes survived in the right trace. This is consistent coloring because that kind of, I guess, northwest node got the color red here and the red color red here. The southeast node got color green. Other nodes appeared here and didn't appear here, or appeared here and didn't appear there, and we're not going to worry about this. Okay, so that's a consistent coloring. And so the idea is if we can find a consistent coloring for all traces, and every pair of nodes is in some trace, then we can reconstruct the original graph. Okay, so let me kind of if this part is like kind of really not technical to prove, but let me just like kind of elaborate what I mean by the theorem statement, and then hopefully it'll become clearer why it's not hard to prove. So let's say I've found my consistent coloring of these 3 graphs, or these 3 traces. Okay, now from these 3, I know there's an edge between kind of the yellow and the blue node, the red and the blue node. I know there isn't an edge between the yellow and the green node. And so I can take all that information from these traces, these three traces in this case, and conclude that, well, between some pairs of nodes, there's no edge, some pairs there is an edge. And if I've never seen, say, the yellow edge and the yellow node and the purple node show up simultaneously, well, I don't yet know whether or not there's an edge between the yellow and the purple node, but after log n traces, every pair will have shown up together or simultaneously at least once, and I'll resolve the entire graph. Okay, so it all basically boils down to how do I find this consistent coloring? Okay, so let's do that. So I'm going to look at the special case where the deletion probability isn't a half, which is how I set up the problem, but I'm going to assume it's kind of less than a quarter. Okay, and the result's actually kind of not too difficult in this case. It's actually kind of extending it to the case when the deletion probability can be a half or greater, where the challenges lie. Okay, but for simplicity, let's try and find consistent colorings, assuming nodes deletions are less than a quarter. So if you think about it, like, you know, this means that
Andrew,
yes.
Andrew, can I ask a question?
Absolutely.
How many colors are you allowed to use?
N colors.
Exactly N?
You will never need to use more than N colors.
All right, thanks.
Okay, thanks very much. And I'm happy to see you can ask me questions. Okay, so if the distance probability is that small, what we can argue is that for any 2 traces, the number of nodes they have in common is greater or equal to n/2. In fact, we don't actually even need exactly less than a quarter. This parameter can be tweaked, but what we're going to need, all we're going to need is that between every pair of traces, the number of common nodes is more than n over 2. Okay, so the lemma that we can prove is that, let's say trace 1, let's say V1 is the preserved nodes in trace 1, and V2 is the preserved nodes in trace 2. And let's say, so V1 and V2 look like that. And let's say U1 and U2, U1 is the subset of V1, and U2 is the subset of V2, where you've maximized the size of U1 and U2 such that the induced subgraph on U1 is the same as the induced subgraph on U2. What this lemma is saying is that with high probability, U1 and U2 actually kind of correspond to the same set of nodes, and it's exactly the set of nodes that are in this kind of overlap of V1, V2. Okay. Okay. So proof or proof sketch, if you like. I guess it's a proof sketch. This is the closest I'm going to get to Ronit's claim that I'm going to talk about streaming. The induced subgraph on V1 intersection V2 is indeed a common subgraph of V1 and V2. But is it the largest? Well, this is where Muller's going to come in. Suppose we found a larger common subgraph between the trace on V1 and the trace on V2. So let's say we had W1 over there and W2 over there. Well, in that case, W1 would be strictly bigger than the size of the intersection. Okay, and the size of the intersection was going to be more than n over 2. So what this would mean is that we would have found a W1 and W2, each consisting of substantially more than n over 2 nodes, such that this graph was isomorphic or identical, if you like, to this graph. And this would contradict Muller's theorem. Okay. So we've managed to conclude the first part that the largest subgraph of V1 and V2, a large common subgraph of V1 and V2 is indeed the graph on the intersecting set of nodes. Okay. Then we use the second part of Muller just to note that U1, this subset of nodes, which is bigger than n over 2, will be asymmetric. So when, let's say people in the audience are looking at their trace and looking at their, looking at the induced graph in V1, and I'm looking at the induced graph in V2, that when we've looked for the largest common subgraph, not only are we looking at the same set of nodes, but that subgraph is asymmetric. So there's a unique way to color or to label those nodes between the two of us. And so we'll end up with a consistent coloring that way. Okay. Let me briefly kind of say the sort of the issues that arise when the deletion probability is bigger, say is a half or larger. In this case, it's I can't guarantee you the full, like it's impossible to pull off the same proof as before, but it seems substantially harder. The issue that we ran into is that we were able to show that if you guys are looking at trace 1 and I'm looking at trace 2, then and we find the largest common subgraph, then the set of nodes upon which your subgraph is based and the set of nodes that my subgraph is based may not be identical, but they're pretty close. Okay, so and they both heavily overlap with this kind of V1 intersection V2. So in this case, the approach is that we can basically you're trying to find a subset of nodes, and I'm trying to find a subset of nodes such that we truly do have this consistent coloring amongst that subset. So what we do is that we both subsample the U1 and the U2. We find this subsampling, if we do it at the right rate, means that we only get we end up with the same set of nodes after the subsampling, and we can color these consistently. Okay, I appreciate that was maybe a little high level for you to nod and say, "Oh, that sounds about right," but that is the truth. Okay, Okay, so let's see, I should wrap up in a couple minutes. Let me briefly talk about adjacency matrices. So, so I'm going to kind of switch models. Like previously, we were just talking about the primary objects were unlabeled graphs. I'm now going to think about fixing an adjacency matrix for the graph and talk about random sub-matrices of that adjacency matrix. Okay, so everyone knows what an adjacency matrix is, hopefully. So for the unknown graph, we can associate this binary matrix. And then when we do a trace with every node being deleted with some probability, so in this case, I guess these two nodes were deleted, that corresponds to the one labeled 4 and the one labeled 6 being deleted. So if we delete the 4th row and the 6th row and the 4th column and the 6th column, we get this, what we'll call a matrix trace. Basically, it's a random principal submatrix, called principal just because we're doing symmetric column and row deletions. Okay, so then the natural question is, well, how many random submatrices are required to learn a graph? Now, this model doesn't seem that different from the graph model, but actually the results, but there's actually a strict separation. Because remember, for arbitrary graphs, we needed exponential in n random subgraphs. But as soon as you kind of you fix this matrix representation, like with this kind of like ordering of the rows and columns, we're able to show that for exponential in n to the 2/3 traces suffice. And I'm not going to have time to go into this, but basically the proof approach is if you kind of cast your mind back to that single slide where I kind of condensed this complex analytic approach for doing mixtures, stroke kind of trace estimation via mean estimation. And you extended that approach to not talking about single-valued polynomials, but to two-valued polynomials with two variables. Set the parameters right, and you get this result. Okay. For sparse graphs, we can improve this upper bound further. So again, for sparse graphs, I'm talking about low arboricity graphs, or in particular, I'm talking about like kind of, I'm going to use the fact that for any subgraph, any induced subgraph of original graph G, there must be at least one node with constant degree. So that's the property I'm going to use. The larger that constant, the larger the arboricity of the graph. Okay, and now this is admittedly super high level, but I want to convey a couple of ideas here. So you could view the proof as kind of reducing the matrices for sparse graphs to string reconstruction, kind of. The idea is that for the unknown matrix, you look at these like the kind of columns below the diagonal, okay? And you look at this in the unknown matrix and the trace matrix, okay? And you find a way to encode these binary strings into values, say x1 up to x6, where xi corresponds to the kind of ith column, okay? And for the matrix trace, like if we're talking about the 4th node and the 6th node being deleted, say this column being deleted and this column being deleted, then we end up with x4 being deleted, x6 being deleted, but also note that these values themselves change. Like, you know, this, the first column wasn't deleted, but the first column did change because some of the rows got deleted. That makes sense. But if you look at this picture, it's kind of similar to kind of trying to reconstruct this string given this trace. And so, like, kind of, basically the core idea is like finding a way for xi to encode the columns underneath the diagonal, where xi prime is the corrupted copy of x. And if we find a suitable encoding, and that encoding is going to be based on results about distinguishing distributions by looking at different moments, and basically appealing the process that we can leverage because it's a low arboricity graph, then we get our result. Okay. So basically this encoding is going to, again, relate to binomial distributions, say x2, which has a 1 in the second parameter and the third and the 4th parameter, is kind of going to be an encoding of the fact that we've got a mixture of a binomial 2,5 and binomial 4,5 distribution. Okay. Okay, so that's the results. Thanks very much for listening. Again, I'm super sorry I'm not there in person. Okay, thank you.
We have a question, but you just have to give me some time to run the mic up the stairs. I'm going to get my workout today. You see, I'm in shape. Thank you so much.
Hi, Andrew. Nice talk. Thank you. I have one question regarding reconstructing adjacency matrices. So when you said you take submatrices, are those only submatrices that correspond to like subgraphs or like just any random submatrix of the original matrix?
We can handle both cases. If the, well, okay, so okay, let's think. Yeah. So yes, I think I can safely answer yes to your question. But specifically, we can deal with arbitrary binary matrices with the rows and column deletions being independent. And we can also deal with a specific case when rows and column deletions are dependent, which does actually add some issues. And of course, a special case is when this arbitrary matrix is symmetric, the zero diagonal, so it corresponds to a graph. So yeah, so everything I said about the arbitrary graph basically doesn't involve that much more ideas than just dealing with matrices, which is actually something we covered in the Krishnamurthy information theory paper.
Okay, perfect. Thank you.
Thanks.
Okay.
Hey, Andrew. So a quick question about the random graph version. When you want to find a, yes, sorry, I'm Sefer, good. So when you want to find a random, like when you want to do the consistent coloring, do you find these common subgraphs by just enumeration, or is there a polynomial time algorithm that do that?
That's a great question. We really didn't look at the computational efficiency. We just looked at the sample complexity. Like, I guess for random graphs, you can tell whether two random graphs are isomorphic in polynomial time, basically because it's almost certain that they're not. It would be interesting, or potentially interesting, to say, is it faster to find the largest common subgraph given it's a random graph? So yeah, so we don't address it. We just say, hey, exponential time, that's fine. But I think that's a good question to look at. And there's maybe some hope, but I don't know how much hope I'd have.
All right, good, thanks.
Thanks.
Any other questions? Yes. Yeah.
Hey, Andrew, this is Sesh here. So if you modify the model by saying that you can, instead of choosing each vertex with probability half, you choose exactly half the vertices at random, it seems that the arbitrary graph result won't hold because that's the reconstruction conjecture. But for random graphs, you would still get the same upper bound. Is that correct?
The random graph, the upper bound would still hold. Would the lower bound hold? That's a good question. Yeah, the lower bound for the arbitrary graph would absolutely not hold or the proof would not go through as I wrote the proof. My gut says like normally fixing the number of deletions to be the expected number of deletions, like normally everything stays the same, but I'm not immediately sure that's the case here. Yeah, okay. So certainly nothing I presented or is in the paper addresses your question. Thinking off the top of my head, I would speculate that you still need exponential and n traces when you have, like when you delete exactly n over 2 minus 1 nodes, for example. But I'd have to give it some thought to prove it.
Thanks.
Yeah, thanks, Ash.
All right, let's thank Andrew again.